We know that carbon dioxide is a byproduct of metabolism. So long as you're living, you're producing CO2. Problem is we need to get rid of it at some point along the line. We talked about the normal oxygen. Did we mention the normal oxygen consumption is 250 milliliters per minute? If I didn't, allow me to do that now. Normal VO2, oxygen consumption, is 250 milliliters per minute. Normal oxygen delivery, if you recall, is 1,000 milliliters per minute. So we're only utilizing about 25% oxygen extraction, about 25% of what we have available, which is good because we have a lot of reserve. The normal carbon dioxide production by the cells is about 200 milliliters per minute, and that's the VCO2. If I take the ratio of the carbon dioxide that is produced comparing to the oxygen that is consumed, we call this the respiratory quotient or respiratory exchange ratio, and the normal value is 0.8.
Is that the thing you use in the alveolar?
Oh, you are so smart. Yes, that is the thing I use in the alveolar air equation, right on target. Which means that it's not entirely a constant. For now, we're going to let it be a constant. Next year will be a little bit meaner. Okay? So that 200 divided by 250 is 0.8. A lot of things in life end up becoming 0.8. So how does the CO2 get from the tissues back to the lungs? Well, there's 6 ways. We know that the carbon dioxide has to come back. We're not one of these species that has the ability to allow CO2 to pass through our skin and get rid of it that way. We have to physically move it back to the lungs. It's the only way that CO2 can be excreted. So there's 6 ways, 3 of which are in the plasma, 3 of which are in the erythrocyte. So if I think of my bloodstream, here's my erythrocyte with hemoglobin in there. There's going to be 3 ways that are in the plasma and 3 ways which are in the erythrocyte. So let's go back and recall this concept of the hydrolysis of water. This is a very important process that we're going to see not only for CO2 transport but for acid-base balance. In the presence of water, carbon dioxide will join with it to form a substance called carbonic acid. Carbonic acid is a very volatile acid, meaning that it can be it can further dissociate into bicarbonate ions and hydrogen ions. Or in the presence of hydrogen ions and bicarbonate ions, it can go the other direction. These arrows here are in both directions. Under normal conditions, this is a very slow reaction. Not a lot of CO2 is converted to carbonic acid under normal conditions. In the presence of an enzyme called carbonic anhydrase, however, that process is speeded up tremendously. So CO2 readily combines with oxygen in the presence of carbonic anhydrase to form carbonic acid and dissociate into bicarbonate ions and hydrogen ions. So let's talk plasma. Inside this, when I have my, here's my cell, and it's producing CO2, and here's my bloodstream. 3 ways that CO2 is going to be carried. Number 1 is it's going to be bound, some small amount will be bound to some proteins that are inside the bloodstream. We're going to form what are called carbamino compounds. Basically the big proteins, albumin, things like that. Very small amount. Some of it will go through that reaction and form bicarbonate. CO2 plus water going to carbonic acid, which dissociates into hydrogen ions and bicarbonate ions. And those are the ones we're talking about. So it's going to be carried as bicarbonate, not as CO2. And the last portion is that it's going to be carried it's going to be dissolved in the plasma, which is what we've already come up to talk about as far as having PCO2, either in the arterial system or in our case coming back to the lungs as a venous value. So far, so good? Okay. That's kind of, I don't know what it is. Ignore it. Pay no attention to that. There you go. This value of PCO2 here and the amount of carbonic acid that is present are directly related. So as CO2 goes up, carbonic acid goes up. There's a proportionality there. This value, carbonic acid, is measured in a unit called milliequivalents per liter, as is bicarbonate measured in milliequivalents per liter. CO2 is measured in millimeters of mercury. I want to go back and forth between the two. So if I take my PaCO2, multiply it by a factor 0.03, I will then convert that PCO2 from millimeters of mercury to milliequivalents per liter. And I'll explain why later, but for right now, that's just the way we do it. So if I have a normal value of 40 PCO2, times 0.03 equals 1.2, and now it's milliequivalents per liter of blood. So, right? 3 ways it's carried in the plasma. Attached to proteins, as bicarbonate, dissolved. There's 3 other ways that it's carried also inside the erythrocyte. The good news is it's the exact same way. Dissolved, attached to a protein, as bicarbonate. So, and this kind of just makes logical sense. If this is my erythrocyte sitting inside the bloodstream, that's RBC. Whatever PCO2 is located inside the plasma is going to be the same as what's going to be inside of the erythrocyte. Whatever fluid is inside there, it's going to have the same PCO2. It's going to equilibrate across the entire process. So some of it's going to be carried as dissolved within the intracellular fluid of the erythrocyte. Bigger portion, though, is going to be carried with a protein, specifically hemoglobin. Hemoglobin is one of those substances that's really magical. Not only does it bind with oxygen in a reversible way, it also binds with CO2. Remember back when we talked about the oxyhemoglobin dissociation curve? When PCO2 levels rise, saturation levels go down. It's called a rightward shift. You can think of the carbon dioxide basically pushing the oxygen off the molecule. Doesn't really, but you get the gist. That little lousy CO2 who just did that then gets on the hemoglobin. It freed up oxygen, so it took the spot. The analogy I've heard described is if you've gone to Cedar Point, you know what I'm talking about. The roller coaster ride comes up, the one door opens and the people get off, and the new people get on. So it's the exchange that occurs between carbon dioxide and oxygen for competitiveness with the hemoglobin. We called this level of CO2 rising, causing the saturation to fall. We call that the Bohr effect. CO2's effect on the oxyhemoglobin curve. Dissolved, carried as with a protein, and as bicarbonate. And we're going to find that this is the biggest component, 63%, is ionized as plasma bicarbonate because carbonic anhydrase is present within the erythrocyte. It's one of the few places in the body that carbonic anhydrase is present. We're going to find out it's also present in the renal tubules, as well as being present in the eye. Dissolved protein, bicarb. The three different ways that it's carried, both in the bloodstream and in the erythrocyte. Now you have this blown up for you in the back. So let me just kind of reiterate what I just, why aren't you there? Where are you? Where's my pen? Vanished. Stubborn. So, my cell is producing CO2. By the way, I have 11%. If you add them up, they have 10%. Yeah, close enough for jazz. So some of it goes into the capillary and is dissolved in the bloodstream itself. We call that PCO2. Some of it attaches to some proteins and forms carbamino compounds. And because there's no carbonic anhydrase present, some is converted to bicarbonate within the bloodstream. Dissolved, attached to proteins as bicarbonate. That same CO2 also goes into the bloodstream. Again, there's a partial pressure of carbon dioxide in the erythrocyte, which is exactly the same as the partial pressure in the bloodstream. It equilibrates. It attaches to a specific protein called hemoglobin. So where the hemoglobin was attached to oxygen previously, that oxygen is freed up, goes into the cell. That hemoglobin now can attach to carbon dioxide. And then finally, the big one is the creation here, CO2 and water forming carbonic acid. Because carbonic anhydrase is present, a lot of it is converted, and bicarbonate is present. How are we doing? Okay. So when this equation is going on, especially in the presence of carbonic anhydrase, we form these bicarbonate ions, but we also form these hydrogen ions. And hydrogen ions are basically proton donors, and we're going to consider it to be an acid. So let me just I'll explain what pH is in a little while, but for right now, there's an inverse relationship between the quantity of hydrogen ions that we have, the concentration of those, and the pH. So as I increase the hydrogen ions, I end up decreasing the pH, and I would consider that blood to be acidic. Conversely, as I reduce the quantity of hydrogen ions present, I end up raising the pH and having a situation where it's alkaline or basic, if you will. Thank you. Now what ends up happening is these hydrogen ions which are created, if you notice, they don't stay inside the erythrocyte. They migrate back into the bloodstream. And they actually form sodium, they join up with sodium to form sodium bicarbonate. So let me go ahead and just redraw this. Here's my erythrocyte. It's producing bicarbonate. In the bloodstream, I have sodium ions and chloride ions that are floating around with sodium chloride. This bicarbonate that was created in large numbers, because there's carbonic anhydrase present, they move out. I have a negative ion moving out into the bloodstream. Now I got an electrical neutrality issue here. I got a negative going out. I have to have a negative going back in, and that's where chloride comes in. So the sodium and chloride split. Chloride moves into the cell, bicarbonate moves out, and now there's sodium bicarbonate formed, and chloride's happy inside the cell.
What drives it to move out?
Because it wants to. It wants to be free.
Makes sense.
No, it doesn't, but it just does. Okay. But this is called the chloride shift, also known as the hamburger phenomenon, because somebody named Hamburger first described it. Don't ask me why. It just is. So that completes this here process. So bicarb moves out, chloride moves in, and we're all happy. Now there's a certain amount of bicarbonate that is within the bloodstream. Okay, before I go to that point, let me just make mention of a normal value here. I don't believe we've talked about this one yet, right? Have we? No, I think we talked about it in 1060 maybe. So you got it all memorized, so it's no big deal. Excellent. Okay. One of the things the body does quite efficiently is maintain the pH in extremely narrow range. From a chemist's point of view, a neutral pH is 7.0. For us, it's 7.4, with the range being from 7.35 to 7.45. So from a chemist's point of view, our blood is a little bit alkaline, but for our purposes, we're going to consider that to be the normal range. There is a relationship that exists between these two things. If you remember, this substance here is created by taking the CO2 and water to form this. It then dissociates in the bicarbonate ions and hydrogen ions. The ratio between how much bicarbonate you have and how much carbonic acid you have is always maintained at a pH of 7 within a normal range at a ratio of 20 to 1. As that ratio changes, the pH changes. So let's go back. First of all, let me go back and make sure we have all of our normal values. We just said this is the normal value for pH in the blood. For arterial carbon dioxide level, 35 to 45. Normal bicarbonate level, 22 to 26. Normal oxygen level, 80 to 100. pH is reflected by this ratio between these two. Now, if you go back a little bit, we said that we can convert this PCO2 to milliequivalents per liter by multiplying it by 0.03. So the PCO2 is directly reflective of the carbonic acid. More PCO2, more carbonic acid is formed. So, pH that goes down, we're going to call an acid. And an acid would be where the ratio of these two is less than 20 to 1. When the pH goes up, we're calling this an alkaline condition. And that ratio is greater than 20 to 1. Let's say my ratio is 18. The amount of bicarbonate to the amount of carbonic acid is equal to 18, the ratio, 18 to 1. First of all, what is that? Acid or alkaline? It's an acidic condition. Okay. How, given this ratio, can I make the number smaller than 20? Decrease which?
pH.
Well, it's going to be a decrease in the pH, yes. But what about the bicarbonate? It's going to decrease. So if I decrease the numerator, I make the overall number smaller. Let me say that again because this is important. As I make the numerator smaller, as I reduce the bicarbonate level from 22 to 26, say down to 19, I'm going to make that ratio smaller. What about the denominator? Increase that. So as my carbonic acid gets larger, or my PCO2 gets larger, it's going to cause that ratio to get smaller. And the opposite would be true for an alkaline condition. So far, I'm okay? Well, I'm always okay. It's you guys I worry about. Okay, hold on to this thought because we're going to come back and utilize this concept when we begin the process of determining whether the acid-base disturbance is caused by a respiratory problem, i.e. PCO2, or by a metabolic component, which we're going to reflect through the bicarbonate level. Okay, so what happens then is I got all this CO2 now loaded into the bloodstream, loaded into the erythrocyte, transporting it back. It comes back to the lungs, and what's got to happen? All those things that we did when we were transporting it reverse themselves. So CO2 is released from the hemoglobin within the erythrocyte. That protein binding goes away. CO2 dissolves back into the plasma and back into the alveolus. And that's what this slide is showing us. All the arrows are basically just reversed in the process. The dissolved component goes away. The protein in the bloodstream goes away. Any bicarbonate that is there through the carbonic acid goes back into CO2 and is eliminated off. Same as all those true within the erythrocyte. Again, chloride now shifts back out, bicarb shifts back in, so the chloride shift is reversed also. And magic upon magic, we're now able to ventilate that CO2 off. Okay. There is a relationship between carbon dioxide PCO2 and the amount of carbon dioxide that can be totally carried. It's a linear relationship. There's no wiggle to the curve. Nothing like that happens. But what does affect is like CO2 affected the oxyhemoglobin curve, O2 affects the CO2 binding capacity. And where it was called the Bohr effect as far as CO2's effect on the oxygen carrying capacity, it's called the Haldane effect. The effect of O2 on CO2's ability to be carried. And this is just kind of graphically showing us that if I look at the PCO2 along the x-axis and the total CO2 being carried along the y, you can see that as O2 levels get higher, less is able to be carried. So as I go up in oxygen levels, the ability to carry goes down. That's all it's saying. And that's logical sense. That's what you would expect to happen in the lung as the O2 levels rise in the pulmonary capillary. CO2 levels want to fall. So it's the opposite of the Bohr effect. And the interesting thing is they're both kind of working simultaneously to accomplish the loading and unloading of oxygen and CO2. All right, some terminology. Electrolyte we talked about previously. These are these charged ions. And we're going to look at ones like bicarbonate as being our important one. The term buffer. The term buffer is basically a mechanism by which acids or bases can be neutralized so there's not a big change in pH. When there's excess acids present, the body attempts to neutralize them because it doesn't like an acid or an alkaline environment. The last thing it wants to do is have extra acids around. So it utilizes substances called buffers. And we'll spend a little time next year talking about specifically what they are. But there's buffers there that say, you know what, I'm going to neutralize that pH. I'm going to take it so it's not as excessive change. A strong acid is defined as one that dissociates completely when placed into water. A weak acid is one that only dissociates partially. I'll show you a picture. And we could have the same thing with a strong base and a weak base. As far as pH is concerned, 7.0 is is a normal distilled water. Blood's a little bit on the alkaline side of that, and you can see as you go down, you get various other things that have very alkaline levels or very acidic levels going in the opposite direction. The degree to which they separate and dissociate from each other, the hydrogen ions, and let's say the chloride ions, the degree to which they separate is going to be called a dissociation constant. And this sentence here is the important one. The degree to which the dissociation occurs. Bigger number, bigger dissociation. And it's got this letter K, but we're going to ignore it. Can you see that the top one dissociates a lot? There's very limited amount of HCl bound together. They're all separated out. That's a strong acid. Strong acid means there's lots of hydrogen ions that are free. Okay? They fully dissociated. Carbonic acid's a weak acid. There's very few hydrogen ions that are left free. They're normally carried within the carbonic acid itself. You see the distinction?
Is that what strong acids are doing when they're breaking down something? They're aggressively binding to it?
Well, the hydrogen ions are basically yes. Yeah. That's why hydrochloric acid is not a pleasant thing. All right. We talked about the fact that this pH is maintained in a very narrow range, and it's maintained that through buffers within the bloodstream itself. Because we know we're producing CO2, and CO2 is going to form carbonic acid, which is going to dissociate into bicarbonate ions and hydrogen ions. Oh, there's hydrogen ions there. I got to take care of them. And the body does, through buffers, maintains a very limited amount of hydrogen ions present. Keeps that pH in a very narrow range. In fact, the amount is so small that we have to use a logarithmic scale as opposed to a linear scale. You know what the difference between a log scale and a linear scale is? It's exponential. Where this is linear, this is exponential. It's got a definite, the more you increase, it gets bigger. The Richter scale for earthquakes is a logarithmic scale. So the definition of this thing called pH is the negative logarithm of the hydrogen ion concentration. What the? Big part, negative, meaning it's an inverse relationship. Hydrogen ions go up, pH goes down, as we just shown. It's logarithmic because we're talking about such a small change in hydrogen ion concentration is going to change pH quite significantly. Okay. Normal value, got it there, we're good by that. And the way that the body controls this, we talked about blood buffers. It also uses our ventilatory system, and it also uses the kidneys. Now let me go ahead and reiterate this. I suddenly have an increase in hydrogen ions concentration, and I have a fall in pH. Almost instantly, blood and tissue buffers kick in. So this is within moments. An attempt is made to control the hydrogen ion concentration. There's only a limited number of these buffers around. So quite quickly they can be overwhelmed. The body then uses the ventilatory system to control the amount of CO2. If I have excess amounts of these, I can go the other way with that equation and convert it back into CO2. Yes? I can then ventilate that CO2 off. So I can control an acidic condition simply by increasing ventilation. The third way it does it is it utilizes the kidney to try and eliminate hydrogen ions through a little bit of a complex problem that I don't want to get into. So this was instantly. The respiratory system works within minutes, and the kidney works within days. So the kidney's ability to regulate hydrogen ions is really slow. The respiratory system, of course it's the best system in the world, works almost immediately. Okay. And again, we talked about the buffers being these things that prevent a big swing in pH. I don't really care right now that you know what they are. But look at that. Man, that substance is pretty cool. It not only carries oxygen, not only carries CO2, it also buffers extra hydrogen ions. Too cool. Okay. You know what? Let's take 5. Is being canceled and one that is listed as being open. So you still should have been able to register.
Because it was saying
Yeah,
all these
this one
are
is.
full.
Yeah. It's because we closed them off.
There was nothing else in the book, though, that I could
Not book.
register.
All right, let me continue on then. and talk about how pH was initially derived. This is one of the mechanisms by which acid-base balance can be evaluated. There's other ones that are out there, but for our purposes, this is the one we're going to use. Uses what is called the Henderson-Hasselbalch Equation, and basically talks about the relationship between, as we said previously, the bicarbonate level to the carbonic acid level. Now, when I drew it earlier, I said, well, it's kind of that like that. Really, if you wanted to calculate it, this is the dissociation constant, talking about the carbonic acid bicarbonate buffering system. Log. I ain't got a flippin' log on my calculator. So the good news is we're not going to worry about it. Okay. What's my PCO2 arterial-wise normal? 35 to 45. Call it 40 for fun, right? Right in the middle. So to make that into milliequivalents per liter, I multiply it by 0.03, and I end up with 1.2. What's normal bicarbonate level? 22 to 26. Let's call it 24. It's in the middle. So 24 over 1.2, right? $20. 20 to 1. Wow. That's where that comes from, just so we were clear. So again, if you were to take the, can we round? Yeah, 7.4. So we can simplify this by saying the pH is bicarbonate over CO2, or we're going to find bicarbonate is regulated through the kidney, PCO2 is regulated through the lung. So alterations in either kidney function or lung function will end up causing acid-base disturbances. Okay, let's go back to our prior values. 735 to 745, we're good there. Greater than 7.45, we're going to call an alkalosis. Less than 7.35, we're going to call an acidosis. Normal CO2 is 35 to 45. When you have a value greater, we say it's hypercapnia or hypercarbia, and that's reflective of hypoventilation. Less than 35 is hypocapnia, or what would be caused by hyperventilation. Remember that CO2 and minute ventilation, alveolar minute ventilation specifically, are inverse relationships. PaO2 is somewhere between 80 and 100. For right now, you don't need to know this, but it is age dependent, that as we age, our normal PaO2 falls. We just become less efficient of gas exchangers. A couple of important ones here. Values greater than 100, we're going to call hyperoxemia. Hyper, above normal. And as far as hypoxemia, we said anything less than 80 was hypoxemic. We're going to go a step further and say between 60 and 80, or 60 and 79 technically, is mild. 40 to 60, 40 to 59 is moderate. Less than 40, severe. So if I measured my arterial PaO2 and I said it was 62 millimeters of mercury, I would call that a mild hypoxemia. So on the test next week, there's 10 questions or 10 blood gases that you're going to have to classify. They're each worth 2 points, whatever. But no, they each are worth 1 point. Yeah. A third is going to 1/3 of that point is going to be classifying the PaO2 as mild, moderate, severe, normal hyperoxemia.
So you would ask what is 75 and you would have to say 9.
Mm-hmm.
Something along those lines.
And it's literally that part of the test you write out. It's not multiple choice. It's kind of a, I won't say fill in the blank, but it is a blank. So we're good on normal values then. All right, let's go for a ride. pH, we said, was determined by that ratio between bicarbonate and carbonic acid, or bicarbonate and PCO2. We said that as that ratio gets bigger than 20:1, we become alkalotic, and that can be caused by either the numerator getting bigger or the denominator getting smaller. So a condition that causes an increase in bicarbonate level or causes a reduction in arterial carbon dioxide will create an alkalosis. A ratio greater than 20 would be caused by a reduction in the numerator or an increase in the denominator. Makes logical sense. Sure it does, Rick. Lie to me. So if you'll notice, there's two different values that keep changing here, the bicarb and the PCO2. Anything where the PCO2 is involved, we're going to call a respiratory problem. Anything where the bicarb is involved, we're going to call a metabolic problem. Baby steps. So, first step in our classification system is quite simple. I look at my pH. I always start at the pH. Is the pH below 7.35 or above 7.45? If it's below 7.35, I'm going to call it an acidosis. If it's above 7.45, I'm going to call it an alkalosis. Pardon me?
Whether it's metabolic or not.
Whether it's metabolic or respiratory. That's exactly correct. Now, one of the things that is present on my website is something called a random generator.